afternoon section. That is, we are going to see the tutorial class. Myself, I am Dr. Sunil Kumar D. I am assistant professor from the Department of Mechanical Engineering, National Institute of Technology, Silchar. So these afternoon sections fully based on the tutorial sections of 2 hours. The title of the tutorial class is Detailed Discussions on Machines and Micro Fabrications in Machining Laboratory. We will be seeing the kind of micro fabrication machines which is available in our laboratory, and we will be do some hands-on experience on micro fabrications. Before starting that one, let me introduce what is machining and what was the advancement from the macro machining to micro machining. The how far we developed based on the technological development and scientific theory. Here we can see the machining is a negative process. The process of removing material from the workpiece in order to fabricate, in order to get a desired shape and size. On the other hand, if you take the welding, that is a positive process. That means we are adding the material. We are adding the material in it. So here you can see that the machining which developed from this macro level to micro level. Here you can see this is a conventional lathe machining. This is a 3-jaw headstroke. Here there is a machining going on, like turning operations going. Parallelly, this is a micro level. Now you can see this is a micro tanning on brass. Brass already we know it is an alloy of copper and zinc. So you see the micron level machining happening based on the scientific advancement in the technology of manufacturing science. So here you can see the micro EDM operations to create slot on the iron foil. This one we will be seeing the hands-on training in our laboratory. After this class over, we will be taking to you in the laboratory to physically you can do the operations such that you will get a hands-on experience on this micro machining one. Is this all the one brief introductions you might know, since you are there are the audience of BTech first year, second year, third year are there. So it is good to me to explain, to introduce the already existing one whatever we have. So this one is a conventional machining laboratory. You can find the lathe machining, milling machining, drilling machining, grinding machining, shaping machining. This machine, the mother of the machinery lab is like lathe machining. These are the following operations you can able to do with the help of this machine. And coming to the advanced machining machines such as like CNC, electrical discharge machining process, wire cut EDM, then laser machining, ultrasonic machining, and electron beam machining. Now again we are in the another era, that is that micro fabrication techniques in machining laboratory such as lithography and micro milling and micro toning and focused ion beam machining, micro EDM and laser micro machining and the additive micro fabrication. This one, the lithography and FIB, gradually we have another 4 days lecture. There are experts are coming on that particular area. You will be having more knowledge on that by hearing that lecture, by attending that lecture. So here, this is one small, I would like to introduce what is FIB. So FIB machining is a highly precise and macro and nano fabrication technique that uses finely focused beam of ion to sputtering action. Sputtering means the removal of the material in the micron level. The sputtering, then milling, which can also help to deposit and at the smaller scale. That is called FIB. So FIB looks like a similar column of scanning electron microscopy. There only one FIB gun will come. A new attachment will be there. In the conventional scanning electron microscopy, there we can have one conventional gun. This is a SEM source. This is the way of removal of the material. Okay. The sputtering means material removal. So it enables the precise milling. So here the typical photograph, it shows that the novel method of preparing transmission electron microscopy sample of micrometer sized powder particle by using FIB. The transmission electron microscopy really helpful to in order to know the size of the precipitates which you have. So the challenge behind the TEM, transmission electron microscopy, is to fabricate the sample for that microscopy technique, because it should be thin film. Electron has to be transmitted and go. Then only that with that pattern we can identify the type of precipitate or the size of the precipitates. For that, these micro machining techniques, that FIB can be an alternative technique. So for fabricating a specimen for the transmission electron microscopy, the conventionally they are doing like some small scale milling, then again radius polishing, then jet polishing they will do, then only they can bring out the sample. But with the advancement of FIB, focused ion beam technique, we can fabricate the specimen out. So you can see this is a 10 micrometer cut. So just imagine what will be the size of the specimen, how precisely they can do. But throughout the advancement in the manufacturing technology, this is feasible here. So here, before starting that FIB, this is a brief of FIB. So here we might heard that of cutting fluid. In all the machining process, there is a cutting fluid we are using. So cutting fluid is helpful to reduce the heat, because if it is simultaneously heating happen, the object, the size of the component may deteriorate. Means the properties of the material may deteriorate. To avoid that one, to make it a cool environment, we are using some coolant, that is called cutting fluid, we used to tell. So cutting fluid having some property, cutting fluid have some thermal conductivity. It should be, it should not be corrosive. It should, like that, some desirable properties are there for the cutting fluid. Here one small work I would like to show you. Here I have taken the machining of maraging steel. I have taken one maraging steel of grade MDN 250. Maraging steel means it's a type of steel material. Maraging means martensite plus aging. Maraging means it's a combination of martensite. The material will be martensitic steel. That aging treatment they have done. Aging means heat treatment. So this is a high strength material. So fabric machining of this high strength material is always challenging, because cutting tool, the conventional machining tool, there is a cutting tool is required, cutting fluid is required. Cutting fluid to save the material. Okay, then cutting tool has to extract out the material. So cutting tool having, since it is a harder base material, one of the criteria for the machining is the tool material should have high wear resistance, high hot. It should be thermal conductivity, highly lower thermal conductivity. These are the criteria that are there. Since the workpiece is maraging steel, harder material, you need to go high-end tool material. So it is the machining cost will be very high. So here we have done that machining with the conventional machining way only, but here we have changed the cutting fluid. There are three conditions we have taken. This is a without any cutting fluid. We didn't apply any cutting fluid. This is a conventional milling tool. This is the maraging steel plate. Okay, workpiece. This is a cutting tool. Here there is no cutting fluid in it. That means we didn't apply any cutting fluid. This is the cutting fluid one. Same milling we have done with the help of cutting fluid. Cutting fluid you might see, it will be like oily base, milky base, like fluid. It will be like this way. You can see the photograph. And third one, this is a cryogenic machining. So you might heard the term cryogenic. Cryogenic term means the sub-zero temperature, right? That is a cryogenic one. So here we have applied some liquid nitrogen in it. During machining, some liquid nitrogen we have poured and we have done the machining. Now, after that, now you can understand three conditions. That means we are changing the cutting environment. Then what will be the properties of material? Whatever the machined material having some property. So we are analyzing that one, whether it is changing without cutting fluid, any problem was there, or with the cutting fluid, any problem was there, with the cryogenic treatment, any problem was there. That one gradually we have studied. You can see this is the without any cutting fluid one. This is milky based one. This one is cryogenic one. You can see clearly, you can see the machined surface showing very finer grains. In the case of cryogenic machining one, we can notice. So you can see this is the EBST, electron backscatter diffraction map. You can see this in the grain orientation wise, all the grains are randomly oriented, but there is a significant difference in the grain morphology. It's clearly noticed with respect to cutting environment. Cutting environment changing, this kind of finer things happening. Okay. So here you can see this is a low angle boundary, high angle boundary map. Here you can see 1 degree to 5 degree, 5 degree to 15 degree, then 15 to 65 degree. Actually, the grain boundary means the two solidification front meets, that region is called grain boundary. Actually, grain boundary are the strengthener for the material. For example, the room temperature, if there is any deformation happening, slip system will move. If there is any grain boundary which will hinder the slip movement, obviously the mechanical property will improve. So the grain boundaries are hindering actions here. The grain boundary itself, based on that misorientation between one grain and another grain, it is further classified as low angle grain boundary, high angle grain boundary. Low angle grain boundary means the theta, the misorientation angle between 1 degree to 15 degree. This combinedly, this red color and the green color, the combinedly together, it is called low angle grain boundary. Wherever the blue color symbols are there, that blue color is called higher angle grain boundary. Okay, these grain boundary fractions, the number of these fractions you can see. In the case of cryogenic one, we got the grain boundaries of higher angle boundary is 46%. So balance 55% will be high angle boundary. But in the case of high angle boundary, only 39%. Here 52. So the boundary, apart from the grain morphology, the fraction of grain boundary evolution also changing with respect to the kind of cutting fluid you are putting. That means cutting fluid playing a major role to change everything. Okay. So here this is called a CAM, kernel average misorientation angle. During machining, machining nothing but some deformation happening. So kind of some stress is developed in it. So this map is showing the strain accumulation in it. Wherever that this is a scale is there, almost everywhere material is strained. Okay. So here this is a phase change. So we are more keen to know, by changing the cutting fluid, is there any phase transformation happen or not? Because it's a maraging steel, some martensitic structures are there. Without cutting fluid, temperature will shoot up always, because there is no, we are not giving any cutting fluid. Cutting fluid will take away heat from the cutting zone. Since there our condition, there is one condition is called without cutting fluid we have to do. So we are more curious to know that is there any phase transformation happen or not. But fortunately, we found that there is no phase change at all. All phases are martensite. You can see the red color symbol is showing martensite. Everywhere martensite only. So that means cutting the temperature, whatever suited up, it is not sufficient to go for the phase transformation temperature. There are some phase transformation temperatures are there. AC1 and AC3, you might be having some basis in material science. You might knowing that AC1. AC1 means the austenite start temperature. Then AC3 means austenite finish temperature. So here, the whatever the temperature was happened during the machining, which is not high enough to change the phase. That is very clear here. Then this is a machined surface. Then subsurface hardness we have taken. We are very keen to know the mechanical property. So we have seen there is a significant difference in the grain morphology. There is a significant difference in the grain fraction, the grain boundary fraction we have seen, but phase change, there is no phase change. But then across the machined surfaces, we have taken the hardness measurement, whether what is a variation in the hardness due to the cutting fluid changing environment. So you can see this is a schematic diagram. We can see top side is a machined surface. There only the milling happened. But the cross section side we have taken for the analysis. You can see this is a Vickers micro hardness tester. This is the depth below the machined surface. That means this is the top area. Then coming slowly we are increasing the area. So you can see that while doing machining, the adjacent area is getting more strained rather than far away from the area. Is it like correct? No? If you are doing machining, the tops are near to the cutting tool, that material will get more strained. But if you take far away from that cutting region, there much effect will not be there. The same thing here, you see that cryogenic one, that blue color line, near the cutting area, the hardness is showing very high because of the cryogenic condition we maintain, that microstructure morphology you have seen, and because of the fraction of grain boundary evolved in it. Okay, but next to the wet condition, but the dry condition is showing very poor hardness in that one. Okay, so that means it implies that if you want to enhance the properties of the machined surface, that means machining time, we always think that if residual stress is going, then some deformation happening, strength should not go down. Always our criteria is strength to retain in it. So if you maintain the cryogenic condition, you will get a good hardness value. Okay, so here one summary of that whatever machined environment. Here you can see the machining of MDN 250 maraging steel. There are three conditions we have applied: cryogenic one, wet one, dry one, and this is the changes in the grain morphology. And XRD pattern, X-ray diffraction we have taken to study the residual stress evolved in it, because residual stress is all the machining, conventional machining process, residual stress is a danger one, because if it is in residual stress are there, then catastrophic mode of failure is expected in the material, because you are not knowing what is the magnitude of residual stress present in it. If you are not knowing, roughly as per the factor of safety 2, you will based on the yield strength of the material, you will start design the material. But whatever residual stress was evolved in it, that one will create the catastrophic mode of failure. So in order to avoid that one, we are more keen to know what will be the residual stress of the material by changing the machining environment. Here you can see the cryogenic condition, the blue color peak is there. Everywhere the peak is there. But the one, if you see minutely, there is some peak shift is there. Peak shift means the peak shift towards the right side means there is a tensile residual stress evolution. You can see this is the peak area. If you see, suppose 42 point something, but the wet condition, red one, little bit 42 point maybe 6. This one maybe 42.8. Like that, some minor shift in the peak. That shift in the peak is telling that the residual stress also altered. That means by changing the cutting fluid, you are getting the difference in the hardness property, morphology is changing, then residual stress also evolving. So this is the magnitude of the residual stress. We have residual stress, we have here the phase identification. From the phase map itself, we understand there is no change in the phase, but there is a peak shift was there. So we are more keen to know what is the magnitude of the residual stress. So we have measured the residual stress also. This is the low angle boundary, high angle boundary, fraction one. Then surface roughness also we measured. Then in that we understand that cryogenic one, where minimum surface roughness is there. That means minimum surface roughness means oviness in the surface is less. In the case of dry condition, without any cutting fluid, if you're doing, oviness is large, like this way, up and down, up and down. So this kind of ovulation, like oscillation is there. From there, it will crack will start, failure will come. So perfect surface finish means surface roughness should be minimum. But out of the three conditions, we have got the cryogenic condition one, surface roughness also very minimum. Okay, that means it's a very clear picture we got. That means the surface is so clean. Okay, so clean and without any much like unevenness. Okay, without much unevenness. So from the study, we noticed that like cryogenic machining is suitable. Okay, this is in the case of conventional machining. Now, so all the problem, whatever happening, you understand now. You see, the cutting conventional machining, what will happen? The cutting tool should have high wear resistance, high strength, everything. In addition to that, cutting environment also playing a role. Correct? But cryogenic one different, wet condition one different, dry condition one different. Now you see the micro fabrication one. In the micro fabrication one, we are going to study that photolithography, all those things. There is no direct contact of cutting tool and the workpiece. How this kind of changes happening? Okay, with the advancement, the technology, the lithography is coming gradually from tomorrow class onwards. You will get that one. Now we will move on to the laboratory classes. There we will have some hands-on experience from the conventional machining technique to from the advanced machining technique. Okay, we will please assemble here. We'll go there for the laboratory. Okay, thank you.